This is ELPI is a programming language. Let's say it's a joint work with several people, and in particular, those ones are the implementers of regional things, and nowadays the language is mostly maintained by us. So what is ELPI? ELPI stands for Embedded Lambda Prolog Interpreter, and it's the only existing higher order constraint logic programming language so far. ELPI is also an implementation of this language written in OCaml, and the E for embeddable is because it has been designed to be easily embeddable in your own favorite interactive theorem prover if it is written in OCaml. If it's not, you can use it as an external library. And right now it is actually embedded in Coq, so you have this Coq ELPI extension that allows you to do metaprogramming in Coq with this language. It is experimentally embedded in Lambda P, in Matita, and the MMT system of Vabe is not implemented in OCaml, so cannot embed it, but it uses this as a compilation target for the experiment.
Lambda Pi is deducti?
Lambda Pi is deducti, yeah, it's one of the two implementations of deducti. So, what is higher order constraint logic programming? Well, it's a push out in a sense of higher order logic programming and constraint programming. And you can think of it as a very high level language to implement an interactive prover. So that it's good for implementing interactive provers and not much else in a sense. And what is higher order logic programming? Well, again, there is mostly one or two languages in this class. Lambda Prolog is what we started from. It is an extension of logic programming to manipulate terms with binders. So it's a kind of Prolog, let's say, where you can manipulate syntax, because you can manipulate terms with binders. And it is a very high level language that is very, very nice to implement type checkers, program transformers, program transformations, things like this, but not interactive provers. So that's why we extended Lambda Prolog to get to ELPI. So ELPI is Lambda Prolog, in fact, plus constraint handling rules. So what does the Lambda Prolog part does for me, and I will show you in the code in a bit. It manages binders, alpha conversion, capture avoidance substitution, all this comes for free. So if you want to interpret, to implement your whole thing, this is for free. It manages backtracking because it's a logic programming. So again, if you want to extend your system and you want to have automatic backtracking, it is for free. And it allows to implement inference rules almost directly. I will implement you in a short bit, show you the code of interactive prover written in ELPI. And we will see that the inference rules are almost there. And what does the constraint handling rule part do for me? It is able to manage suspended goals, which are proof obligation, and let me combine and simplify proof obligation. So, in a sense, is what I need to go to an interactive paper where we have proof obligations. And what I can do with it, I can implement rapid prototypes of interactive provers. I can give the user an expressive language to express domain-specific knowledge, so tactics, unification in type classes, are all things that are very easily implemented in such a language. It lets the user tamper with the implementation of a system, and it adds a powerful macro language to your prover or metaprogramming capabilities to your prover. This is, for example, why it is embedded in the pocket now. So are there some significant experiments? Well, I'm just citing a few to give you an idea. So, for example, we implemented a type checker for Landau's Grundlagen in Automath. There exists a fast OCaml implementation, which is called Helena. We've implemented it, and the results are something like this. So, we are 3 times lower than interpreted Helena, we are 2 times lower than interpreted Coq, and 12 times lower than compiled Coq, because ELPI is an interpreter, it's not a compiler, so we should compare to this. What is Tejas? And we are very much faster than Tejas. Well, Tejas is the official compiler for Lambda Prolog, is a well-known compiler for Lambda Prolog. So we have a subset of Lambda Prolog, we are an interpreter, and we are 50 times faster than the compiler of Lambda Prolog. So this is sort of nice. We also have implemented, for example, a kernel for Matita 09. It is much more simpler and modular with respect to the native OCaml code, and it goes 8 to 15 times lower than the OCaml implementation. So you cannot, if you want to have speed and you don't want to do prototypes, it's not the good language. Okay, you can be much faster with with other programming languages. But if you want to design a prototype, that's very nice. As I told you, it is an extension language for Coq for doing metaprogramming. For example, the hierarchy builder talk of Cyril, well, that thing is implemented in ELPI. And let's see a demo. So what the demo has two parts. I don't know if I will have time to go to the second part. So what I do in the demo, the first part is implementing an interactive prover for System U in 142 lines of code. So I will first implement the kernel, the type checker for System U in 65 lines. Then I will add, for example, coercions to see how to tamper with the things like you usually do in a T1 prover. I will add an elaborator plus unification hints in 40 lines, and finally a prototype of a REPL, 3 tactics, and minimal automation in 29 lines. Okay. The second part, if I will ever get there, otherwise you can ask me private. So I will also try to implement a translator from System U to System F. At a certain point I said, well, I'm not really sure about a couple of lines, so it is actually bad. And so the question is, you are implementing things with ELPI or with Lambda Prolog, how can you be sure that what you implement is correct? So how can you prove your implementation correct? And the reason is, if you are in the Lambda Prolog fragment, then you can use the Abella C1 prover that is especially useful to prove Lambda Prolog programs correct. Okay, so first part, I implement an iterative prover. Second part, I use a prover to verify in the time that part of my implementation is correct. Okay? So let's go to the first part, and let me add something also. Another thing that is nice of the language is that it is maybe the only language that you don't know the syntax, but you already know the operational semantics. And indeed, I'm usually able to teach it to students in a couple of hours, because they basically know the semantics, they just don't know that they know the semantics. So let's see why. So first thing first, ELPI is an untyped language. Lambda Prolog was typed, but our implementation is untyped, but you can still add types if you want, and they are checked if you add them, otherwise not. So here I've added some types to help reading. So I declined type means I'm declaring a new type. So I'm declaring a new type term, which will be the type of the terms of System U. And now I'm adding constructor for these terms. So an application takes two terms and returns a term. Okay. So far so good. Star is a term. Star is a sort. Okay, it's a sort of System U. The other two are more puzzling at first view. So lambda abstraction is what? Lambda abstraction takes the type I'm abstracting over, and then it is a binder. Okay, so how do I represent binding in Lambda Prolog? Well, I use the meta-level functions, the meta language. So the idea is that I'm reusing the meta language to implement a sort of half-deep, half-shallow embedding of my thing. So I take a function of the meta level from term to term, and this represents the body of my lambda abstraction. And the same for the hardware type, which is really pi. Okay, it's what written hardware is pi. So just to let you understand, if I want to represent something like lambda x of type t, x applied to x, I encode it this way. So it's a lambda abstraction of over type t, and then I use a meta-level function from term to term, and this is a meta-level abstraction of lambda Prolog. So it means a lambda x dot, and I return an app of x to x. Okay, that's how it works, and there is some nice syntactic sugar in a sense. It's really the grammar of the language. I can omit this parenthesis, so I can write lambda tx slash up xx, which means it looks really like lambda is binding x in the rest. But really, it's just this function space. And the function space in this programming language is not used to do computation. I will not compute, it's not a functional language. The function space is just used for binding. Okay, for representing bindings. And the application of this function space is just for substitution. Okay, substituting something in place of the bind. Okay, also another observation. Okay, this is my grammar of term. Something is missing. Variables. there are no variables in my representation because, again, I'm using the meta-level variables to represent my variables. Okay, a variable stands for some missing term, and variables at meta-level will do the job. And also note that there is this is not an inductive type. Okay, this is an open type. I'm not saying that these are the only constructors of subterms, and indeed I can add later as I want more things to the thing. It changes the way you prove your program correct, and indeed Abella does something a little unusual because it doesn't have inductive types. Now let's move to implementing the kernel. So I need a series of judgments. Here I write in the usual informal style. Here is the corresponding ELPI code. So the first one is type inference. Given a type, a term t, I'm inferring its type. So t is input, t is output if you want. And I'm using off. So off is a predicate proposition over two terms. So it takes two terms and it is a proposition because it is a judgment. What is missing? Gamma. Gamma is totally missing. So in all my judgments, I will not have any gamma. Why? Because again, my gamma will be pushed to the meta level. So gammas in a judgment usually is a set of assumptions you have. But since this is a logic language, the assumption can be at the meta level. So you will never see the gammas, but we will use the gamma somehow. The other predicate are type checking. So I'm given in input both a term and a type, and it must check. It holds the judgment if the type of t is tie up to conversion. I have local variable declaration, t of type that I write lvar t tie, and this will be the context entries. This will be the assumption that I will put in the meta level in place of putting them in the gammas of my judgment.
The first argument of lvar is the name, or?
No, there are no names. Yeah, if you want, is the name. So I'm saying this term has this type, and I will use that for fresh variables. So in a sense, this term will be the name of the variable.
Why can you not use isa? Why do you need to split them?
There are reasons. So I could use is a or off, but I'm also using for I will implement several things. So I don't declare one. But yeah, I could. And finally, I have a predicate for one-step beta reduction, for multiple-step beta reduction, for conversion, and so on.
Why isn't the this local variable declaration, since this is sort of scoping over all the things that follow it, shouldn't it also be some kind of meta function?
No. When we see the typing rules, I think it's pretty clear. Okay. So now let's move to implementing the thing. So this is how the code looks like. In comment for some rules, I've written, let's say, what you expect to see on paper, what is the translation with the syntax, which is basically the same written below. So let's start with this one. This is the first rule. To check that tie as type tie, I infer a type prime for tie, and I check if type prime and tie are convertible, even as missing tie. Okay? So just changing to here my notation, this is off, this is conv, and this is a. So it would be just this inference rule. Now, the lambda prolog code in this case is exactly the same. It's just that the conclusion of the rule is written here. This, as usual in prolog, means its implication from right to left, so it means the premises imply the conclusion. And the premises goes up here, and the comma, like in prolog, is and, is a conjunction at the meta level. Okay, so this is just writing this rule, and this is nothing different. Yes?
Can you remind me, off is infer and is a is check?
Exactly. Exactly. And note that there is no gamma, and also note that some variables are all uppercase, which means that they are schematic variables, or they are universal quantified, if you want, in the rule. Okay? This is the second rule. It says, for example, informally, if I have declared x of type t in gamma, then I can conclude that x of type t, and I say I can conclude that x of type t if I can prove x tie. And how can I prove it? Well, I will prove it because I push these things to my knowledge base in the network. Let's see one rule with the binders to understand better how we use these things. So So what? Yeah, let's do this one first. So let's take application. So the informal rule is usually this one. I take m applied to n, I infer the type of m, I reduce it to a pi type, I check that the argument is type A, and I conclude B where I replace n in place of x. Okay? So what happens in lambda prolog is the thing written above or written here, is the same thing. So first I infer the type n and p, is the same. Step 7 is one beta reduction, and I reduce to error AB. This error AB is this. A is the type A, but the B here is the function at the meta level lambda x b of x. Okay? So I check that n was type A, and now I want to conclude that the type is B where I put n in place of x. But B here is a function, it's a meta level function from x to something. So I can just apply B to n, and that's a substitution. Okay? So wherever you see a substitution in an informal rule, it's just an application here. And finally, let's see the rule for lambda abstraction, because it's interesting, because it pushes something in the context. So the rule goes like this. I want to prove that the pi type over A, type A of lambda y b of y is a star. If A is a star, and it's okay, and now it's the interesting part, I have to add to the context the fact that for some fresh variable x, x is type A, and I have to check that the B, where I replace x in place of y, is a star. Okay, this is a usual rule for typing these things in system U. So how it translates? Well, I say error B as type star is A is a star, and that's okay. And then I have this line. So what is this line? So this is a meta level. This is meta level implication and meta level pi type for all, if you want. So I'm writing for all x, if I assume that x is type A, I have to prove that is A B of x star. Okay? So why is this equivalent to doing this? Well, now let's come to the operational semantics of this language. So I'm putting all these actions, this is my knowledge base, and then I make a query, like in Prolog. I can make a query and the system recursively try to prove my thing. And the rules of the rules it uses, the operational semantics of the system, is just the usual rules you already know for natural deduction, basically. So if I ask you to prove f and g, it proves f and it proves g, so it splits the proof search in two. If I ask him to prove that there exists an x such that f, it uses the existential introduction rule. It doesn't know yet what to put in place of x, so it put a meta variable that will be unified later during the proof search. Now, this is a rule that interests us now. What if you want to prove for all x f? So the for all introduction rule you know by logic is you pick a fresh y and you prove that f, you put y in place of f, x, and you prove f. And that's exactly what happens here. And for implication f imply g, you put f in your context, which is not written explicitly, it's just a set of things you can use, and you go down to prove g. So if we go back here, that's exactly what happens. If I ask the system to prove this off for some concrete arguments, well, it will try to prove these two things, so it will split, and then it will try to prove this. So first, it will generate a fresh name for introduction rule. Then it will put in the meta-level context this assumption, that is the act here, and finally it will go back to try to prove this. Okay? So basically, that's why I'm saying you know the operational semantics. Operational semantics is just natural deduction rules for a fragment of natural deduction, which is large enough, and with something more. Okay? So these are the rules. Now let me go quick. Of course, you have a rule for doing one step, doing multiple step, doing beta reduction. So for example, let's just look at the beta reduction rules. So usually it's written like this. G of n reduces to something if G reduces in many steps to a lambda abstraction and I substitute n in place of f. And the rule becomes exactly what you expect. So G of n reduced to f of n if G reduces in many steps to a lambda abstraction, and I can, and my output is a substitution of n inside this function.
What's this equality doing here?
I could have written fn there. It would have been logically the same. By doing this, I'm first doing this and then doing that, which helps a little bit the determinism of the proof.
When does the stuff on the left get done?
When?
Well, like when you have things in the conclusion, like when are they sort of performed? Like how does that work?
Yeah, they are never performed. So this is a query. So you're proving this.
But like you could have like in your application rule, for instance, you had a application on the result of this of when you were typing an application, you put fn up there.
Where I'm typing an application here.
Yeah.
You mean when this when this computation is done?
Yeah, like it's not pattern matching that, right? It doesn't say, oh yeah, when I'm trying to prove of, I need to make sure this is enough.
Well, as soon as it basically this is an application in your meta level, and as soon as B becomes concrete, it's reduced up to. I mean.
So it's allowed to apply this rule even though it doesn't know yet.
Yeah,
that
exactly.
But you could have written it the same way.
Yeah,
so
I could have written
Bn and then
exactly.
Bn equals B applied to n later on.
Okay, so there are not many rules more. There are the usual rules for conversion, and I'm done. So now I can test my system. So, for example, here are some tests. So I assign to T this lambda term over here. I try to check if T is type, and what is the type of S, and I can just run it. Yes?
You didn't configure any input and output for your...
No input, no output, okay? So, if I run, for example, that thing, test one, kernel, okay, if I run test one, T tie kind, here it is, it has computed the kind and the type of the lambda term by applying my rules. And it also asks me, do you want another solution? Because it can backtrack. So if I ask for another solution, there are no other solution in this case. Okay? So far so good? What time do I have to finish?
Oh, well.
While you compute, let me show something else. So, okay, so that's the type checker. So if I give it in input a full lambda term, a fully specified lambda term, it can compute the type and so on. Now the question is, what happens if I feed him a lambda term that contains a meta variable, like x here? So what is a meta variable here? A meta variable means inside my lambda term there is a part of the lambda term that is not specified. I'm putting an x and I'm asking, is there any x that can fill it this lambda term? So it's a lambda term with missing part inside. And if you take Kavi hour, the way you are used to, what is a lambda term with a beta variable inside that can stand for something else? If a lambda term is a proof, a lambda term that contains some meta variable to be understood is a partial proof. Okay? This is what partial proofs are, the way they are implemented in Coq, Lean, and so on. And in particular, that XABF means X represents a missing part of my proof that can use A, B, and F, which are the scope, which are the variable bound by the lambda abstraction. And now, what happens if I ask the system to run this test? So I'm running this recursive judgment over the lambda term. It goes lambda, it goes lambda, it goes lambda. It will reach the meta variable X. And now, which rule is applicable? I have a rule for lambda abstraction, rule for variable, rule for application, but I want to know the rule, the type of a meta variable. And here kick in the usually generative semantics of prolog, which means it will try the first rule and it will unify your meta variable with a variable, or if it tries the second rule with an application, and so on. So basically, it will automatically search and synthesize terms that have a type. This is exactly what happens.
Wait, is this X can be unified?
Yeah, it can be unified. Everything that is uppercase is existentially quantified in a query, so it can be unified. So if I run the second test, it gives me a solution. So here it was lambda, 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 and then a term. And here it is lambda, 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 and then it has used one of the variables that were available. And it has synthesized the type. If I ask, do you want another solution? Yes. Oh, now it's different. Now it's put a star here. No, it is picking another variable. I want another, yes, C0. I want another, star. I want another, I put an error, and so on. So basically, it's randomly enumerating lambda terms that are well typed. And of course, maybe an automatic prover, but a dumb one, and it's not what I want to do. I want to implement an interactive prover, not an automatic prover. So I don't like this behavior. And also, it could even diverge. In this example, it doesn't. But if I take the third example, it's very similar. So I have lambda abstraction and I have a term that is to be instantiated. If I run the example, it found a solution, now it is diverging. Because it's trying to enumerate the terms in a very stupid way and it can diverge. So that's another reason why I don't want it to automatically find the terms for me.
I think you might have already answered my question, but there are no guarantees as to like the order in which you print these out or whatever it might.
Well, it depends on the way you list your clauses in the term, but it's hard to control, let's say. Okay, so lesson so far. So this is lambda prolog. There is no, this is the lambda prolog fragment of ELPI. You can do very nice implementation of things defined with judgments and inductive rules, but if you want to handle something interactive, that's not a good language because it doesn't allow, it has this generative semantics. This is where the constraint programming part kicks in. So, let me go here. So, what are the changes we want to do? Well, what happens like in Coq or so on when you are using a meta variable or an underscore in your term? So you are asking to infer its type or to check its type. The procedure goes recursively, as is done here, but then it reaches the meta variable. So you reach the meta variable with a constraint, something like this meta variable that has access to these variables must have this type. And this is recorded. So the system stops and adds this constraint to this set of constraints. And what constraint it is? It is a typing constraint. It means the things that I will put in place of the meta variable must have this type and can use some variables. And I've added to my context the fact that these variables have certain types. This is a sequence. This is a goal. Okay? The goal you see in a proof assistant with the hypothesis and the conclusion is exactly the typing constraint you get in ELPI. So what I need to do, and this is what I can do in ELPI, I tell the system that when the recursion arrives on a meta variable, it has to stop. Instead of generating randomly solution, it has to stop and store that goal, the constraint, as a constraint. So there will be a set of constraints, and of course, if later the variable is instantiated, the system will resume this query and will check, or backtrack. So how do I do it in the ELPI syntax? Well, I do two things. Let's go to off, for example. I do two things. First, I indicate a mode. So when I explain you the off predicate, I told you it has an input and two outputs. but I didn't tell the system. So basically, it is the way I intended to use a predicate. So now I tell the system. So mod of IOO are keywords. I and O. It means off is meant to be a predicate where the first argument is an input and the other two are an output. So if you want, it's also a way to say I'm doing recursion somehow on the input arguments, and I'm generating the output argument. Yeah.
I think there's a different of than before. The previous of only had 2 arguments.
Yeah, sorry, because I've skipped one file. Yeah, and now yes, sorry, I've switched to, I skipped something, so now I've already switched in intermediate steps to an elaborator. So it takes a term to be well typed, and it can modify the term, inserting coercion or things like this. So it has 2 outputs, the modified term and the type. So, and I've added a few rules to this. Okay, so the first thing is I tell the system what is input and what is output, and the second rule is I tell the system that when it's asked to what is the type of a meta variable, this uvar keyword means I found a meta variable of the language and I'm recurring on it, and the meta variable is called x, then I declare a constraint. So when I found the meta variable x and I want to know if it is type y, I put a constraint in my set of constraints saying that once x will be instantiated, I will check if it really has type y. And this means this constraint is suspended over x. So it will be resumed once that x becomes instantiated.
You said is A was check. So why are there 2
Yeah, so maybe would I expected off to become an off instead of an is A, but the reason is that here you are in fact, so here you are doing off, so you're doing type inference, so you get to a variable, and the B and Y are meta variables also, are output. But X could occur non-linearly in your term. So maybe sometimes occurs with some type, and sometimes occurs with sometimes convertible to it. So to take conversion in account, I resume as an is A, because maybe the 2 occurrences will be instantiated in a different way. So the type that is needed here maybe is only equal up to conversion to a type that will be inferred later.
Does uvar mean strictly a unification variable, or does it cover flexible terms?
Let's say all kind of flexible terms. Unification variables apply to things. Okay, so that's the line I've added basically, and I add the similar things to every predicate. All the rest of the code is the same. I'm not changing anything. And now I can do this thing. Yes.
You had a constraint which was the exclamation point. What does this mean?
The bang is a cut of prolog. So it's a way to say when you pass after a bang, you're pruning your backtracking. So you're saying I've taken this decision, do not backtrack here. It's the same semantics of the cut in prolog. So I'm saying if I don't put the bang, I can backtrack and again go to the generative semantics. So I'm saying this is the only choice. Okay, so with this I can write, for example, this test where I put the existential. So I have a type basically, and I'm asking to check if some term which is completely unspecified as this type. So it becomes a constraint, and I can basically use lines corresponding to tactics to advance in the proof. At every line, I'm doing a little bit of assignment to the thing. So let me very, very quickly show this. So on top of that, I just add these lines. They are not much. It's just a top level of my language, and an interpreter for tactics. So for example, I'm saying intro just builds a lambda, apply an application, exit a term, and so on. And what I'm left is with an interactive prover. And I can use a demo while it takes the last question. valvar ELPI interactive, and it's called interactive execution. What didn't it like? Oops. Well, maybe I can just take the question and avoid the typical demo effect. Yeah, there is a parsing error. I must have introduced some parsing error somewhere. So, okay.
Okay. Are there, well, maybe we should thank the speaker.